Hi, welcome to Statics with Grace. So for today, we're going to be talking about internal forces. Now, what we've done up until this point in statics is talked about how external forces and how your reactions or what's kind of stopping your structure or your member from moving under the influence of some kind of external load. Okay, so up until this point, it's just basically what you see is what you get. As we are progressing in statics, we're going to be focusing a little bit more about what the member actually is doing. So once you move on from statics to strength of materials, what you're going to be looking at is basically the effect of your external forces on your member and how the type of member affects how the member or the structure will react. Okay, so right now we are picking up whatever is going on the outside and we're moving it to inside to kind of determine what kind of loads are going on inside. Okay, so what we are trying to do is basically this. We are trying to ensure that the member is able to resist the external loads applied to it. So if you have a simple member like what we have over here, this is a fixed member. So fixed on one side is cantilevered. There's nothing else going on the other side in terms of reactions. But we have some extra forces. We have P, external force concentrated at point C, and then we have some kind of P2 or another load that's at an angle. It's probably a different magnitude. At this point, that's not really our main focus. Okay, so in order to find the internal forces, what you want to do is find every single external force first. Okay, so to get started, looking at this fixed cantilevered beam, if we draw all the reactions, we see that we have a horizontal load AX, vertical load AY. The direction doesn't matter, as we've already talked about. If you do not know what the reaction's magnitude, or you don't know anything about the force, just draw a direction and find out if it's right or wrong. And then we also have an external load M at A. Now this is different from summing moments at A. It's just telling us that for a fixed beam, that we are not allowed to move in the horizontal and vertical, and we are also not allowed to rotate. So once we do that and we're able to find our reactions AX, AY, MA, and P1 and P2 already known, which means we found all our external loads, we are now going to go inside. Now this is a very, very important part of this latter part of statics, because the behavior of the beam or the member depends on what's going on inside. Okay, so what we do is that if we want to find out what's going on at point B, we're going to make a cut. We're going to make a cut at point B. And what that does for us is that we're able to split it into two and see what's happening. All right, so the first thing that's happening inside any kind of cut member is kind of like how a fixed member looks like. There are three things going on. There's a normal force, there's a shear force, and then there is moment. Now, what's really cool about all of these is that these N, V, M are able to be used to find some kind of stresses, and that's something you don't have to worry about for right now, but some kind of stresses that describe the behavior of the kind of material you're using. So we had moving a step, we looked at external, we're looking at internal, and then from there in strength of materials, you're actually going to be using those internal forces to be able to describe what's actually happening on the inside in terms of stresses, which I've written here on the side. So a normal force is going to be some kind of perpendicular force, perpendicular to the surface you're looking at. And shear force is going to be parallel to the surface you're looking at. And then bending moment is obviously a moment. So it's going to be either going in a clockwise direction or counterclockwise. These three forces together on each side should have the same magnitude. MB should be the same MB for the left or right side. And if you add them together, MBs should end up being 0. VB, the two VBs should end up being 0. And then the two N's should end up being 0. That's as simple as it is. Make a cut, find out what's going on the inside, sum the two, and then make sure that the two sides are equal to 0. Once we're able to do that, what we're doing is that we're taking what you seemingly outside right here, and then we are able to translate it or transform it to whatever is going on the inside, which we need to be able to determine if our material is actually going to fail or not. Okay, so the first thing, find external loads and support, find all of them. Then you make a cut, which we've done at point B, depending on where you're trying to look at. and then depending on what you're trying to look at. And then the last part is that we're going to pick a side of the member that we want. So it's either we pick the left hand side or the right hand side, some moments and forces and all the stuff that we've done before, and that should be what's going on the inside. So to get started, we're going to pick a little bit more of a challenging first example, and the reason why I picked this is because I kind of want us to walk through the one that's not immediately intuitive. So on Blackboard, I have posted 3 different examples, and this is basically the last one. Okay, so it's saying that find the internal forces at point J when alpha equals 90 degrees. Okay, so if you're looking over here, we're saying that basically this force is vertical, or alpha equals 90 degrees. So to get started, remember what we want to do is find our reactions, right? So we're going to label all external loads, which I've been doing, and hopefully you'll be learning from that. I'll actually go ahead and change this direction. So we have By and Bx. And then if you recognize AC is just a cable, which means it can be represented as a force, and that we'll call that FAC. And we also know that 780 is another force over here. So to find our slope or directions, we know that it's 240 plus 480, which gives us 720. And we have 600, so 600, 720, that's basically saying 512. I'm sorry, 300 and 720, so that's basically saying 5, 12, and 13. All right, so now that we have that, the first thing we're going to do is sum forces. We're going to find all our reactions, okay? So we care about Bx, By, Fac, because without that, we cannot solve our problem. And since we are finding the internal force at point J, once we find our reactions, we're going to make a cut at J, because that's exactly where we need to find our normal, shear, and moments at that point. All right, so some moments about A. And what we're doing with summing moment about point A, which is right here, is that we're going to be eliminating a bunch of things at once. You'll see that FAC goes straight through A, BX goes straight through A if you track their line of action, which is very nice, because then only thing we have to worry about is BY. So summing moment about A, we have 780, which is this force right here, newtons times cosine 90 degrees times 720 minus By times 300. That's equal to 0. And that what that will actually tell you is that By is equal to 0. Okay. So we find that our By, which is right here, is equal to 0 because of alpha, which is 90 degrees. So cosine of 90 degrees, which gives us a horizontal version, is also equal to 0. All right. So the next step is to sum forces in the y direction. So in the y direction, we have FAC times 12 over 13 minus 780 newtons, which we have over here, times sine 90 degrees, and that's equal to 0. Okay. Since By is equal to 0, we're not even going to include that, and that's why we're just skipping over that. And that gives us FAC is equal to 845 newtons. So summing forces in the x direction, we have FAC times 5 over 13 plus 780 newtons times cosine 90 plus Bx equals 0. We know that cosine 90 is already equal to 0, and that tells us that Bx equals negative 325 newtons. Okay, so if we look at our initial direction, we have Bx going towards the right. It's actually Bx, and I'm writing down purple just to show that that's what the answer is. It's going in the opposite direction. Okay, so coming back here, we know that Bx is equal to negative 325, By is equal to 0, and FAC equals 845 newtons. All right, so now that you have this, we're going to make a cut. We have a cut right here. Pick whichever side. Now, for this question, it's actually much easier to pick, let me shade that in black, this side. Okay, so if you're making a cut, we're making an imaginary cut, we could have picked the black side or the purple side, and whichever one of the two you pick is actually, it doesn't matter. It's just much easier for us to visualize the right hand side or the top right hand side. All right, so if you're going to make a cut, a point J, and we're picking one side, top left hand side. So we have our free body diagram of the cut that we've made. Okay, we know that there is 325. You know that's actually going in the opposite direction, 325 newtons. Okay, perfect. And then we know that if we're making a cut, that we have horizontal normal force going in the perpendicular direction, NJ. See that's going away from the surface. And then we have our shear force, V sub J. And then we have our moment at J, M sub J. Okay, so that's really nice. And then going back to the drawing, we see that it's 480 millimeters going that way. Okay, and then just to get started, that's what we're going to stick with. Now, if we're looking at 325, there are two things that you could do. You could either stick with the conventional X and Y axes, or you could actually rotate it. So you have your X axis here, Y axis here. Whichever one of the two options you pick is absolutely up to you. Now, it's much easier for me to just rotate my angles. So I'm going to change that color. So I have 325 times the slope, which is 5/13, and that's equal to 125. And then I also have 325 times newtons times 12/13, and that's going to be 300 newtons. Okay, and that's much nicer because guess what? Life is much easier for us. Summing forces in the X direction. This is my new X. Okay, so summing forces in the X direction, you can see that we have V sub J, and then we have 300 newtons going in the opposite direction. So we have V sub J minus 300 newtons equals 0, which tells me V sub J equals 300 newtons. Simple as that. Summing forces in the Y direction. We know that Y direction is now going slightly off vertical. So we have N sub J, which is going in the negative direction, minus 125 newtons, which tells me that N sub J is equal to negative 125 newtons. And then changing my color to purple, which tells me that N sub J equals 125 newtons, but it's actually going up. Okay, and then finally we're going to be summing moment about point J. Remember, this is our point J, so summing moment about point J. We have 325 newtons multiplied by the vertical distance, plus M sub J equals 0. If you come back here, you'll see that 325 multiplied by the perpendicular distance, 480, can be some moment about J. Everything else is running through point J, so it doesn't matter, which gives us moment at point J as negative 156 Newton meter, or as I do in my trusted purple pen, equals 156 Newton meter, and it is going in the clockwise direction. So as a little bit of a recap, let's quickly go through it. That if you have some external force, the way a member will behave under a load depends on the type of material it is. Now that's way down the road. We don't have to worry about that for right now. But for the same shape of a beam, if one is made of a material that's completely different from one, if I put a force of 100 pounds on it and a force of 100 pounds on the other one of them might fail and the other one might not fail. We don't know that, okay? Even though they are literally the same member, but because of the type of material. So what we want to do is look at what the external force is doing on the inside as a first step. From there, we're going to start in strength of materials, worry about how the internal forces and loads affect the kind of member it is. So for whenever we have an external load, we're making a cut at a certain point, we have three things going on. Normal force, which is perpendicular, shear force, which is parallel, and then bending moment, which is obviously a moment, so it's either counterclockwise or it's clockwise. Now remember that whichever side you pick, both of them must add up to be able to equal to 0. So VB going down, so V sub B going up should end up being equal to 0, and that's what causes equilibrium. So for a problem like this, what we want to do is find every single external reaction first. Once we found all of those, we're going to make a cut, pick whichever side is easiest for you. We sum moments about a point and then some forces in X and Y direction. That's as simple as that. Internal forces, once again, very simple topic. Do not overcomplicate it for yourself. And put in some questions. Let me know how things are going. Let me know if you need any help with something so I can help you out. Have a great night.